I don't know if you ever find yourself in the part of town where somebody comes up to you and says, "Hey handsome, you want to know about magnetic monopoles?" So I was thinking, I was concerned about this, that maybe you would be approached in such a way, and rather than hearing about them from somebody with a needle in their arm, I thought I would, you know, take a stab at explaining to you what the big fuss is about and whether we've actually got them now and all of the game is over. So here's a funny thing though. I was telling one of my students that I was going to make this video about magnetic monopoles, and he said, "Magnetic monocles?" And he was pretty excited. In this case, we're talking about magnetic monopoles, and you need a little bit of background first. You take some bar magnet, it's got north and south, and you slice it in half with a big green knife, and you're like, ksh, and then you get a north over here, and a south over here, and you're thinking, wow, there's just one pole over there and just one pole over there, but lo and behold, you get a south over here and a north over there. So you get more magnets by cutting your magnets. Awesome. It doesn't happen with dollar bills. But you can cut this again, and ultimately you zoom in on this and you find that there's this chunk inside here called a domain, and inside that domain there are a whole bunch of little magnets, and they're all perfectly lined up. That's a domain inside of every bit of ferrous metal, and that's a, if the domains are lined up, then you get something like a bar magnet, a magnetized hunk of iron, for instance. In this domain, you've got little spins, and each of those spins ultimately comes from an electron or a proton. So if I zoom in even further, I'm gonna say that that's zoomed in from there, and if I zoom in on one of these guys, I've got a magnet, and that's actually a north pole and a south pole right there, and the fact that it's a magnet comes from the fact that there's some spinning happening there, and it's quantum mechanical spin. But this is just, for instance, let's think about it in the case of iron, this is just one electron that's not canceled out by all the other electrons, which is why my fingernail is not magnetic, because I've got a whole bunch of magnets pointing that way, and a whole bunch of magnets pointing that way, and some that way, and the equal amount pointing that way. Anyway, most stuff is not magnetic because the electrons are all perfectly canceling out their spins. But iron is one of those three awesome elements that has the net magnetic moment for each atom. But here you got an electron. The problem is it's got a north pole and a south pole. So even electrons themselves are dipoles, and you just want one pole, you want a monopole. Well, the trick with that is you could go back to Maxwell's equations from the 1800s, and Maxwell's equations forbid magnetic monopoles. Forbid is not really the right word though, the white word. The white word? It's not the right word because they just don't acknowledge magnetic monopoles because they haven't been discovered. So in Maxwell's equations, for instance, one of them says that if you take a surface integral of the magnetic field out of some area, out of any area, then you're always going to find that magnetic field never comes out of an area. So I guess what that's saying is if there's some surface surrounding some volume, if there's magnetic field going out here, then an equal amount has to be coming in. So that means there's no source of magnetic fields that isn't also connected to some sink of magnetic fields. They have to go out and come back in by the same thing. But if you could find something that had just magnetic field, like let's get you another surface over here. This is a Gaussian surface. If you found something where magnetic field was just coming out and no field going in, then you would have a magnetic monopole. And that would be really exciting. Here's the reason it would be exciting. There's the grand unified theory and superstring theory, and these two theories of the universe predict that they ought to exist. And want to know something else cool about magnetic monopoles? The other thing that's cool about magnetic monopoles is that if we had them, oh gosh, there are so many cool things. If we had magnetic monopoles, then Maxwell's equations would be completely symmetric. And I know that you like symmetry. You know, when somebody has a stroke and they're like happy on one side of their face and the other side of the face is all droopy, and this guy got a nice bright eye over here and the other eye's like, moo, and their nose is all chipper on this side and the other side's like, moo. That's not symmetric. Nobody likes strokes, nobody likes asymmetry, nobody likes the fact that there aren't magnetic monopoles that have been found yet. So here's the thing. If we also, you guys remember Paul Dirac, right? Dirac says in 1931, he says, hey, it would be really cool if there were a magnetic monopole somewhere in the universe, because just a single magnetic monopole means that all electric charges would be quantized. Why would that be fun? Well, let's write that down, what Dirac says. Dirac says, here he goes, just one magnetic monopole means all electric charges quantized. Why is that so cool? Oh, because all electric charges actually are quantized, and to have a reason why it has to exist would be a really nice thing. It would be really nice to be able to say, oh yeah, that's why electric charge is quantized, because right now we're sort of like, well, it is quantized and I don't really know why. Okay, so people will be getting really frustrated because we haven't found any magnetic monopoles yet, and there are some suggestions for why. Magnetic monopoles seem to be really, really, really big. And now you're thinking, wait a second, aren't really big things easy to find? Not necessarily, because Einstein reminds you that E is mc squared, so if something's got a whole bunch of mass, and I guess when I say big, I mean really massive. Really massive things take an enormous amount of energy to exist. So creating one in a lab, I mean actually creating a physical magnetic monopole, would take an amount of energy that we haven't been able to dedicate to our super colliders yet. So we need to make a bigger machine, right? The biggest machine in the world, the most expensive machine in the world, is that LHC over in Europe, and that's spinning things around and running them into each other and using the energy to create new mass, which is enabling us to study some things that can exist in the universe, but we need higher and higher energies to see more and more massive things. That's cool. Remember the Higgs boson? Yeah, that's fun. We should make a video about that too. Okay, so you don't panic, but you're just like, man, it'd really be nice to find one. So there are some people who've been working on sort of magnetic monopoles, and the next video is going to talk about exactly what they're doing, but I'm talking about actually getting a magnetic monopole. And what I mean is, if we find a magnetic monopole, it will actually be a distinct elementary particle. You know, you can make the effect of a magnetic monopole, and there's some really good wording. It says that what we have made recently, they've made a basically a rubidium soup of, I guess you would call it a Bose-Einstein condensate, and that's when all the atoms are kind of working all together, and it's a very large quantum system. Really cool stuff. This is a happy Bose-Einstein condensate, and these are the things that can slow down light and ultimately stop it and stuff. Really cool stuff. But they've made a Bose-Einstein condensate, excuse me, that, quote, contains phenomena that are mathematically analogous to magnetic monopoles. So it's not a magnetic monopole because that would be a new type of matter with the E is mc squared, and it would actually exist, etc. And it would also quantize all electric charges, which would be really cool. But we don't have one yet, but we have something that acts exactly like it. So it's like my 2-year-old is sitting in the house, and I say to her, sweetie, I'm really hungry, and she goes and builds me a hamburger out of Legos, right? And you know, the only problem with hamburgers made out of Legos? They're not actually hamburgers. So right now we have a magnetic monopole, quote unquote, that's being built out of a Bose-Einstein condensate. It's not a magnetic monopole. It doesn't taste like one, it doesn't quantize all electric charges in the universe, but it sort of acts a lot like a magnetic monopole. So we call it a quasi-particle. And you can make these out of lots of things. What I mean is you can make quasi-particles of lots of other things, but remember, the building block is ultimately the Bose-Einstein condensate, just like this hamburger is not a hamburger, it's built out of Legos. Good luck if you're hungry. So I already told you internet punks that electric charge has to be quantized if a signal magnetic monopole exists in the universe, but you didn't believe me, so I spent my Friday afternoon going back to the paper. We're talking about 1931, we're talking about Paul Dirac. Let me tell you, here's some advice. You're given a good name like Paul, and you're a man, and everything's fine. Now, I could see why I'd be a little bit embarrassed about his middle names because they were rather French, and he was a British gentleman. But you don't start going by all 3 early initials because that spells Pam. Anyway, we'll take Pam's word for it. Pam in 1931 presented this paper. This paper is described as one of the defining advances in quantum mechanics. This is about 6 years after quantum mechanics had kind of been established, and he spends the first couple pages of the seminal paper here talking about, essentially rambling about electrons and positrons, protons and antiprotons, which hadn't really been experimentally verified, but he'd proposed them theoretically, and blah, blah, blah. And then he comes out with this whammy of a sentence. He says h bar, which is Planck's constant divided by 2 pi, times the speed of light over e squared is 137. Has something to do with alpha, right? But he's saying that is quantized charge. He says that's what we know already. We've got quantized charge by that relationship right there. And here he sets out to associate that with magnetic monopoles, the presence of them. So then he spends, do you want to go to the punchline right away? No, let's not go to the punchline yet. He spends 4 pages explaining that arbitrary ambiguities in the phase of wave functions are independent of the function and therefore depend on the nature of space in which the function exists itself. So here's this wave function, right? And it's got a phase which he likes to describe. He's going to call this phi naught or something, and then multiply it by some e to the I something, I don't know, lambda or something. That's not what he called it, but that's a phase of the wave function. He's saying if you go around some space and then close it back up, then the function itself can have any value, but the phase is dependent on the space that you enclosed. So it's telling you something about space itself, the field of force in which the particle moves, and that suggests something interesting about the nature of space itself. So things really begin to get nasty on page 8, and I'd like to explain to you here's one sentence that he wrote. He said, this is essentially just Weil's principle of gauge invariance in its modern form, and that freaked me out a little bit. I don't want you to panic, though. He begins to conclude that the flux here, the flux out of or into this space, remember we could have some source of electromagnetic field which would then cause a net flux. Here we've got flux going out, here we've got flux going in, and here we've got flux going out again. So every one of these lines is actually leaving that space. Then he begins to say that the total flux is the change in phase during closed interval. So if you're closed integral, if you're doing an integral around this surface, of course it's got to be a 3-dimensional surface, then you could find the change in flux. But that's a problem. There's a contradiction here because we can have n times 2 pi, because there's something about going into, I don't know, some sinusoidal function or something. What he's saying is, if we would like to identify that as the case, we've got this ambiguity which could be off by 2 pi or 4 pi or 6 pi or 28 pi or something, some multiple of 2 pi, which depends on what's inside this space. And then he, I mean, this is kind of a moment of panic, because you say then that the integral of the closed path around this space doesn't have any meaning, but it sort of does, because it could be off by 2 pi, and you start to try to, I don't know, quantum is all about quantizing things, breaking them into, this n is very, very important. But what we're trying to do is, oh, excuse me. Problem is, now the integral can't be the flux from the electromagnetic field. So he introduces the concept of nodal lines, and I hope you've seen these before. A nodal line is a line where there's a 0 in the electromagnetic field. No, not the electromagnetic field, in the wave function. So there's a wave function that he's trying to integrate along right here. And he was saying that the wave function doesn't affect the value, but now it sort of does. So this nodal line is the most important thing. If we've got this space that we're integrating around, a nodal line could be a place where there's a 0 and it could go right through, and we could have the nodal line go forever. And that's the normal case, I guess. So there's a 0 right here, but what's really interesting, so this would just cancel out and that'd be fine, but what's really interesting is we have some space right here and we're integrating around it, and there's a nodal line that ends inside it. That is a singularity in the electromagnetic field. So that could be a magnetic monopole. That's the end point of a nodal line right there. If ends singularity. You probably like singularities because they represent black holes, rips in the fabric of space-time and stuff. But I'm not talking about that kind of singularity. I'm talking about something that is infinite. And I guess the magnetic field of a point magnetic pole is infinite right there. And then, so that's really cool. What he's saying through all of this is that if an electron moves in the field of a magnetic monopole, which of course would extend through all of space, if one exists in nature, then its field extends through all space. If an electron moves through that field, its motion can only be described by a wave function. That would mean it's only real if that electron has quantized charge. That's his conclusion, that the charge of an electron may very well come from the presence of just a single magnetic monopole. Then he does a simple example, and on pages 10 through 12, his simple example, that's a 3-page example for those of you who are counting, his simple example presents this differential equation. This is one of my favorite differential equations, and you could find the general eigenvalue if you want to, but I just want to point out that we've got a couple partial derivatives, and then we're differentiating with respect to phi twice, and then there's also a differentiation with respect to phi once. And we have not just 1 over sine and 1 over sine squared, but also I times the secant square and square of the tangent. And anyway, lambda's some number. So that's cool. I thought that was a rather simple example. You should work through it. Oh, the solution is a separate paper by somebody else. So as he's finally concluding on page 13, Dirac says, here's Dirac's concluding thoughts. He says, quantum mechanics does not really preclude magnetic monopoles. And so I'm going to write mag monopoles okay with quantum. This is a big deal. That is okay. And then he says, one would be surprised if nature had made no use of it. I love this perspective of physicists. They discover something cool in math, and they say, probably real, because it's so cool. So if there's this structure by which charge would be quantized, and by the way, we've seen quantized charges, etc., and nature could make this happen, then nature's probably going to do it. You know, based on what I know about nature, it takes advantage of all the cool things that could possibly exist. He also makes a final celebration that says electricity and magnetism are now perfectly reciprocal. There's a reciprocity between them, and if you take, well, yeah, I don't need to go into that anymore for you guys. If you're watching this video and making any sense out of it, then you know that this guy can turn into that guy and that guy can turn into that guy in a very symmetric and beautiful way. And then he finally says, wait, why don't we see magnetic monopoles? So his proposal, and this looks like he was just tacking this on to the paper right before he mailed it in 1931. Why are they missing? He said that the force between them, this is the attractive between, let's see, I'll put a couple E's in there for you, between magnetic monopoles is 4,692, you know, quick calculation, 0.5 times that between a proton and an electron. So he's just saying you haven't pushed hard enough. That's why you haven't seen them, suckers. In summary, Wikipedia has it written like this, in SI units, which are far preferable to the nasty units that Dirac was using. I'm just kidding. SI units are really inconvenient if you're a theoretical physicist, but I'm not a theoretical physicist, and I become uncomfortable in strange units where C is 1 and stuff. But here's the argument presented by Wikipedia. Wikipedia says there is an electromagnetic field around a magnetic monopole, right? And classically, we have momentum density from a Poynting vector, right? And we have total angular momentum, which is proportional to the charge of the electron. and the charge of the magnetic monopole. And independent, oh, this is a big deal, and independent of separation. And then in quantum, right? In quantum, angular momentum is, of course, quantized. It's quantized in quantized in units of h bar. So that means if angular momentum is quantized, and if that and Qm has some value, then we've got QE also quantized. It's really that easy. Because we know that angular momentum must be quantized, and we know that the angular momentum around some magnetic monopole would be the charge of any charges that are in there multiplied by the charge of any magnetic monopoles that are in there, and maybe some constants multiplying right there. But that gives us this relationship. Let's do it in infrared, where we can conclude that the charge of the electric charge multiplied by the charge of the magnetic monopole over epsilon naught times h times c square is an integer. That's a win. For the win right there. It's usually presented as h bar with a 2 pi on top, but I think that's lame. Let's just cancel out the 2 pi. Bye.